Sure. Here's your passage with punctuation added for clarity. Pulsars are most popular for their crazy rotational speed. Well, really, in light of the fact that now analysts at the College of Sydney have found a fairly peculiar representative of these neutron stars, which turns around its own pivot at a confusingly relaxed speed. Specifically, the item takes an entire 6.5 hours to finish a solitary revolution. This makes it one of the slowest pulsars known, but also a galactic difficulty. As a matter of fact, this strange heavenly leftover with its radio heartbeats turns essentially everything we thought we had some awareness of pulsars topsy-turvy. Thus, it happens that, as indicated by our current hypotheses, this divine body shouldn't actually exist. Even in the vastness of space, everything reaches a conclusion at some point. But then, an end can also be a new beginning. When a gigantic star offers goodbye to the grandiose stage in a dangerous cosmic explosion, it leaves behind a neutron star in a hot, ionized gas cloud. What's more, subsequently, an object that is one of the most outrageous heavenly collections of all. Although the heavenly remainders, which basically comprise of neutrons, generally have more mass than our Sun, they are frequently a couple of kilometers in size. As a result, smaller heavenly remainders are the densest items in the universe, later black holes. But that is not in and of itself an expansion. Neutron stars also have the property of holding the precise energy of the original star and packing its attractive field within themselves. Anyway, due to their minimization, the spin of the neutron star speeds up such a lot that from that point on, it no longer requires several days for it to rotate around its own hub, but only seconds or parts of a second. And while all pulsars are neutron stars, not all neutron stars are pulsars. These are described by the fact that they produce their radiation in a limited shaft, very much like a grandiose beacon. When this light beam radiation clears across the Earth, it can be registered due to the spin of the pulsar as a customary beat of radiation. Subsequently, the name. So far, so natural. However, now, an examination group led by astrophysicist Manisha Caleb from the University of Sydney has identified a pulsar that can with certainty be described as a snail with a limp. But it makes the unthinkable possible. More specifically, this all refers to the fact that the object discharges radio waves, even though it should not be able to do so. In this respect, the theory says that a neutron star that finishes not even one upset each minute is basically not capable of this. But the newfound heavenly leftover estimates an incredible 6.5 hours for one revolution. An object that shouldn't exist, followed with the help of the ASCAP radio telescope in Western Australia, and given the scientific name ASCAP J1. A mission identified during an everyday practice observation presented itself to the specialists as a rotting burst, whose brilliance dropped by 95% in only 15 minutes. Anyway, around then, astronomers didn't yet know that the corresponding source emanates intermittent radio heartbeats. Later, a solitary burst had been registered during the first observation. To reveal more insight into the enormous dimness, the specialists depended not just on additional perceptions with ASC application but also on the Australia Telescope Compact Array and the Meerkat Radio Telescope in South Africa. In the course of this, 2 radiation beats were to be recorded at time spans hours from one perspective. This was joined by the realization that the source has an intermittent nature and, on the other hand, that the object shouldn't actually exist in this structure. Neutron stars essentially transmit radio heartbeats by converting their rotational energy into radiation. Over time, however, they lose energy and dial back. A laid-out theory says that a neutron star should stop emitting radio heartbeats at one point, that is, at around 1 revolution each minute. And yet, the curious pulsar that enlightens the universe at a comfortable speed of 1 turn in 6.5 hours is there. Most pulsars, which turn at a far higher speed, are like spotlights that only shine from one side. That is to say, the pivot around which they turn is closely aligned with the pivot of their attractive field, so we can only notice the eruptions from one attractive post. But in around 3% of all pulsars, and this is the interesting thing, the revolution and attractive tomahawks are nearly at right angles to one another. And that means that we can see the eruptions from both posts. These intriguing double streaks, which specialists call interpulses, consequently provide us with a unique understanding into the math and attractive field of the heavenly body. Whether the attractive and rotational tomahawks of an easing back pulsar turn out to be pretty much aligned is, however, an open research question. But the interpulse of the newfound article could assist us with breaking this secret. In fact, the pulsar radiates another, more fragile heartbeat around 3.2 hours after its primary heartbeat, but with different properties. As indicated by the specialists, this unequivocally proposes that we are managing the radio emanation from the inverse attractive post. This reality likewise makes the divine body the first known snail pulsar to discharge such middle-of-the-road beats. Albeit this main serves to extend the inquiries regarding its beginning, how could the incomprehensible be made sense of? But what do the specialists have to say about this enormous irregularity? Is there any methodology that can make sense of the evidently unthinkable in an intelligible way? Well, yes, there is, but it's muddled. However, priorities straight, the main hypothesis depends on the suspicion that the item addresses a magnetar. We could thusly be managing with an exceptional type of pulsar that is described by a very extraordinary attractive field. Specifically, the attractive field of a magnetar is around 1,000 times more grounded than that of an ordinary neutron star. And also, they create their radio heartbeats by a different component that could maybe empower them to emanate even at lower revolution speeds. However, even magnetars have their cutoff points, and their periods are normally measured in a flash, not in a few hours. But even in the field of stargazing, special cases sometimes affirm the standard. And for this situation, the exemption has the logical name 1E161,348 to 5,589 hours and really produces radiation, but it's X-ray radiation, not radio heartbeats. Considering this, some analysts accept it's almost certain that the unexplained heavenly leftover doesn't as a matter of fact address a magnetar. What's more, besides, not so much as a neutron star. Rather, as per the other option speculation, it very well may be a white dwarf and thus a little, extremely smaller old star. More specifically, white dwarfs are the hot centers of red giants that remain when they shed their external shells. And to be sure, white dwarfs turn substantially more leisurely than neutron stars. But no single separated agent of these divine bodies has been seen to produce radio heartbeats. This is intensified by the way that concentrates on other frequency ranges have up to this point given no proof to the presence of a white midget at the heavenly area being referred to. Thus, it turns out that, as things stand, only one thing can be said with outright conviction about the foundation of the peculiarly sluggish article. It is an out-and-out secret that has left specialists scratching their heads. In light of the fact that regardless of what the heavenly body eventually goes out to be, it will modify part of our galactic rule book. The abnormal mix of slow pivot radio heartbeats and middle heartbeats is driving scientists to re-evaluate the attributes of neutron stars. And it yet again advises us that the universe still has many energizing amazements in store. This applies not exclusively to the universe's most relaxed outgrowths but additionally to the far edge of the speed range. Truth be told, it wasn't so quite a while in the past that stargazers likewise tracked down a record-breaking quick neutron star that twirls north of 40,000 times around its own hub within a solitary minute. The quick Gonzalez of heavenly leftovers is best to be as careful as possible. Neutron stars, because of their gigantic gravity, sometimes come in double frameworks where they frequently redirect colossal measures of material from their heavenly accomplices. Since this frequently results in occasional explosions of high-energy X-rays, specialists additionally allude to such neutron star accomplice matches as X-ray binaries. And now, one of these X-ray doubles has underlined its record-breaking aspirations in two ways. Situated around 26,000 light-years away from us, the team is made out of a neutron star that is as it were 12 to 16 kilometers in size but weighs 1.4 solar masses, and a white dwarf that is about the size of Earth but altogether less gigantic. To figure out more about the strikingly little pair, however, J.S.A. Wells Group at the Technical University of Denmark endured 5 years investigating it using the nicer X-ray telescope aboard the ISS. And in the process, they uncovered a few gigantic shocks in guideline. The purported motions, or at the end of the day, the slight fast variances in X-ray force that happen during the radiation blasts, can give us basic data about the speed of a neutron star's turn. And on account of the double star being referred to, the wavering showed that the neutron star pivots an extraordinary multiple times on its own hub. Also, that's each second, mind you. In other words, the item makes an incredible 42,900 subsequent perceptions are required before the speed record is officially shared. But the second part of the double framework also seems to be setting new cosmic guidelines. Specifically, the white dwarf requires just 11.4 minutes to complete one revolution around the neutron star. Anyway, the fast orbits include some significant pitfalls. Since the heavenly leftovers are extremely close to one another, the neutron star can extract an especially enormous amount of helium from its accomplice. This helium then, at that point, amasses on the surface of the neutron star before its thickness surpasses a specific edge and finally sets off a nuclear blast. Throughout these emissions, the neutron star tries to please multiple times more brilliant than the Sun, and its surface swells by around 50 kilometers. And if you maintain that our recordings should beam on your YouTube landing page later on, you're welcome to start a membership episode now. Just click on approval and subscribe so you never miss another video from us again. We'll see you soon.